Tension and pulley problems is going to be the topic of this lesson in my brand new general physics playlist, which is going to cover a full year of university algebra-based general physics. Now we're continuing on with applications of Newton's laws of motion. We're going to set up free body diagrams. We're going to set up the net force or sum of the forces equations, and just do a whole bunch more problem solving. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. All right, so diving right into tension force problems here. So, and simply put, tension is just the force in a taut rope or a cable or a piece of wire. So, and basically, if you put like an inline spring scale in the middle of that wire or that rope or that cable, whatever it reads, that would be the tension. And it's everywhere the same in that piece of rope, cable, or wire. So, and it usually pulls on both directions. Whatever two objects it's attached to, it's applying a tension force on both of them, but typically in opposite directions, as we'll see. All right, so first question here. So a single wire supports the weight of a hanging 10.0 kilogram mass. What is the tension in the wire? And so we're simply going to set up free body diagrams the way we have been. This one's nice. It's going to end up being just a one-dimensional problem. So, but on this 10.0 kilogram mass, we've got the tension pulling up on it, and then we've got its own weight pointing down. Now, if you look at that tension of that rope again, it's everywhere the same. Now, if you said, well, what's the tension, what is the force of tension on the ceiling from that cable right there or that wire? Well, in that case, it'd be the same, but it would be pulling down instead. And that's what we said where, like, if there's a cable or a rope or a wire attached to two objects, the tension for both is typically going to be the same, but in opposite directions. So here, relative to that 10.0 kilogram, that's how we're going to solve for this tension. We'll label it customarily T. If you have more than one tension and they're not equal, typically you'll use like T1 and T2. So, but here we'll just use T. In this case, this object is not accelerating, it's not even moving, and so we're in equilibrium, and Newton's first law is going to apply, and so the sum of the forces equals 0. And in this case, tension points up will make it positive, its weight points down will make it negative, and so we're going to end up with T minus mg equals 0, or the tension force simply equals mg. Add it to the other side. And now we'll substitute in, so we got 10.0 kilograms, 9.8 meters per second squared. So in here we can see, do this one in our head, 98 newtons, but we're given 3 sig figs on the 10.0 kilograms, so we're going to make that 98.0 newtons to match up with the 3 sig figs there. All right, so similar put question here, but with two cables, and it says, two identical wires support the weight of a hanging 10.0 kilogram mass. What is the tension in each wire? So now we're told they're identical. They're each going to exhibit a tension, so on that 10 kilogram mass. And since they're identical wires in every respect, we're going to assume that the tension in each is the same. So we don't have to label these T1 and T2. They both exert the same tension on this 10 kilogram weight. And we still have its own weight pointing down here of mg, but once again, this lovely 10 kilogram mass is in equilibrium. It doesn't have any motion whatsoever. It definitely doesn't have an acceleration as a result. And so the sum of the forces, once again, equals 0. But instead of just one tension, we now have 2 times the tension, minus mg pointing down, equals 0. So 2 times the tension equals mg. So 2 times the tension equals 10.0 kilograms times 9.0 meters per second squared. So, and again, that's 10 times 9.8 is 98, divided by 2. And we see the tension is just half as much. And again, to get 3 sig figs, we'll make it 49.0 newtons. Okay, so these aren't too bad. They're nice one-dimensional problems, but we can definitely make this harder, and we are about to. So let's take a look at a two-dimensional tension problem. So in this one, we've got two wires of identical length support the weight of a hanging 10.0 kilogram mass. What is the tension in each wire? Well, now these wires don't perfectly pull in just one dimension, just say the y dimension. They pull in the x and the y. So if we take a look at our free body diagram, again, relative to our 10 kilogram mass, it once again has its own weight, mg. So, but then we've got a tension pulling in the wire that direction, and a tension pulling in the wire that direction. Now they're at the same angle, they're identical wires. We can assume once again that those tensions are indeed equal. So no big there. We don't have a T1 and a T2, just T. So, but now we've got to break those up into components to find out how much is in the X and how much is in the Y direction. And so in this case, we're going to have so much of this one in the X direction, so much of this one in the X direction, and then so much of this one in the Y direction, so much of this one in the Y direction. So and if we look at where that 60-degree angle is, this is an alternate interior angle. So this is also 60 degrees if you want to look at it that way. And so this is the opposite side, and as it should be. So we've got our angle with respect to the x-axis at 60 degrees, and so sine is going to be used for that y component. And so in this case, we're going to end up with tension times sine of 60 degrees on this side, but also tension times sine of 60 degrees on this side. And if we cared, and we don't care too much here, as it turns out, we're going to have tension times cosine of 60 degrees there, and tension times cosine of 60 degrees there as well. And we can see that those are equal in magnitude in opposite direction, and they obviously are going to negate each other and stuff like that. But these two don't. And so in this case, we could set the sum of the forces equations both in the x and y directions. But if we want to solve for tension, we're still going to end up doing that in the y direction. So some of the forces, once again, this object is in equilibrium. It's not moving. It's definitely not accelerating. So it's in equilibrium. Some of the force equals 0 according to Newton's first law. And we can see here that the total forces here are going to be 2 times t sine 60. So minus mg, and again adds up to 0. So again, these both point up, so that we made them positive, and mg points down, we made it negative. So and now we can go ahead and solve for that tension. So we're going to have 2t sine of 60 degrees equals mg. So, and in this case, I'm going to kind of start combining some things. So the mass was once again 10.0 kilograms. Gravity is 9.8 meters per second squared. And now we're going to divide this by 2 times sine of 60 degrees, dividing it through to solve for that tension. And now we've got to let our calculator do the work. Probably not doing this one in our heads here. All right, so 10 times 9.8 divided by 2, and either put that all in parentheses or also divide it by sine of 60 degrees. And we are going to get 56.58. And again, to round that to 3 sig figs, we'll make that 56.6 newtons. Based on the numbers we're given, 3 sig figs is appropriate. Cool, so not too much harder. And once again, we could have set up one more equation here if we wanted to. So, and in the x direction, wouldn't help to solve this answer, but in other problems it might. And so some of the forces in the x direction also equaled 0, and I guess I technically could have put that in the y direction. So, and in this case, we would have had t cosine of 60 degrees, making this one positive. We'd have made this one negative, point in the opposite direction, right versus left, minus t cosine of 60 degrees equals 0. And the reason is, obviously this would have just canceled. We would have had 0 equals 0, and there'd be no way to solve for tension. And so we didn't bother setting it up. It wasn't going to help us solve for tension in this case, but we could have set it up had we needed to. And again, in some other problems, we might come across some two-dimensional tension problems where it is necessary. Let's take a look at one last example. All right, so this last tension example we're going to look at is actually a two-body problem. And students usually struggle with these a fair amount more, but it works the same way. You're just setting up 2 free body diagrams, one for each of the objects in the two-body problem here. So this one reads, 2 masses of 4.0 kilograms and 6.0 kilograms are connected by a rope. And they're being pulled along a frictionless horizontal surface by a 60.0 Newton force. What is the acceleration of the blocks? What is the tension in the rope between the masses? Now, notice it asks, what is the acceleration of the blocks? Well, they're attached by a rope, and as long as that rope remains taut, they're going to move together and therefore accelerate together, and they're going to experience the same acceleration. So that's why I didn't have to ask individually, but it could have said, what's the acceleration of the 4 kilogram box, or what's the acceleration of the 6 kilogram box? It would not have mattered. They have the same acceleration. And then the second question is, what is the tension in the rope between the masses? And again, that tension in the rope is everywhere the same. And it pulls on each mass with the same magnitude, but in opposite directions, as we'll see. All right. So again, this is a two-body problem. We can technically set up free body diagrams and some of the force equations for both of them. So if we take a look at the object on the right first, we can see that it's going to have a tension pulling back, so to the left. And then also it's going to have its own weight. And actually, let's do this in green for a second. So it's going to have its own weight, mg, and a normal force there. And we're ultimately going to find out we're not going to care about these. There's no acceleration overall in the y direction. We're going to find out the normal force just simply is equal to the weight. That's also going to be true over here, different mass over here, and a different normal force, so it turns out. But we're not going to care about them in either case, just as an FYI. All right, now for the other box here, we're also going to have a tension now pulling to the right instead, but it's the same tension coming from the same rope, just pointing in the opposite direction for this guy. All right, so we've got some of the force equations we can set up for both. And again, we could set them up for the y direction. Let's say if we wanted the normal force for some reason, maybe if friction was involved, but we're told it's frictionless. And we're essentially, those aren't going to help us at all in solving for either the acceleration or the tension. Notice the tension operates in the x direction, and the acceleration overall is going to be in the x direction as well. And that's why we're going to start with the x direction. If it turns out, let's say friction was involved, we found out we needed a normal force, then we'd set up the y ones as well. But turns out we're just not going to need them. So in this case, we'll start with the one on the left here. So in this case, sum of the forces in the x direction. And in this case, in the x direction, it's not an equilibrium. We're told we're solving for some sort of acceleration of this, and we can see that that has to be true. We've got a force pulling it to the right. There's nothing counterbalancing that force since it's on a frictionless surface. There's nothing pulling back. So the sum of the forces is going to equal ma in that x direction. And if we see the only force that's acting is that tension force, and so that's going to equal max here. And we'll take this one step further. So we got to keep in mind that that's specifically that 4 kilogram mass, specifically in this case. Cool, but now we've got two variables and only one equation. We've got tension, which we don't know. And we've got the overall acceleration, which we don't know, both of which is what we want, but we don't know them. Okay, let's move on to setting up the same set of equations for this guy. And once again, sum of the forces in the x direction is going to equal ma. Again, not in equilibrium. So in the x direction, it will be accelerating to the right. So Newton's second law applies. And in this case, though, we do have two forces. We'll make the 60 Newton force positive. So, and the tension pointing back the other direction negative, so minus tension. And in this case, the m specifically, we got to be careful here, is 6.0 kilograms. And once again, times that acceleration in the x direction. Now, a couple quick things. When I originally wrote these, I have max and max, and it might be proper to maybe make these m1 and m2, especially if we didn't know the masses. We want to make sure we label them properly because they are definitely not the same mass. So, but in this case, we were going to fill in a number anyway, so it wasn't the biggest deal in the world. And from here, we've also got two variables. We've got tension and we've got acceleration in the x direction for both. But the key here is that now we have two variables with, two unknowns, two variables, and two equations. And so we can solve a system of equations here to solve for them. So easiest way to probably do this is to realize that this one's already solved for tension, and just to take and substitute it in against the same tension, it's the same rope, so it's the same magnitude, and just substitute that in right into the other and then solve for the acceleration, and then plug it back in maybe here and then solve for the tension. All right, so here we're going to have 60.0 newtons minus, and then we can see that that's going to be where that 4.0 kilograms times acceleration in the x direction gets substituted right back in, and that's going to equal 6.0 kilograms times ax as well. All right, and so then we'll take and add the 4 times the acceleration over to the other side, and we're going to end up with 60.0 newtons equals 10.0 kilograms times the acceleration. So divide through by 10, and we can see that this acceleration is going to equal 6.00 meters per second squared. All right. So, and the truth is, when you look at this, you're like, well, that force is having to pull all of this weight, technically. So it shouldn't be too surprising that it works out the same as if it was just a single 10 kilogram mass with there being no friction or anything else to worry about in this case. And so 60 newtons pulling on a total of 10 kilograms, yeah, would give it an acceleration of 6 meters per second squared. But this is the proper setup, though. Don't just assume you can always add them together like that, although it's a nice little shortcut in this case. But with a two-body problem, you've got two free body diagrams, two sets of sum of the force equations. In this case, we only set up the x dimension equations. We didn't even set up the y's. It's not necessary in this problem, but we could have. And so not only did we set up just one set of equations here for each, we actually could have set up two if it were necessary. All right, so that's the acceleration. We've still got to go back and solve for the tension. And the key is we can go back to either one of these equations and plug it back in here for the acceleration or here for the acceleration, and then either solve for the tension there or the tension there. And it's definitely far easier over here. So that's what we're going to do. And so we're going to have tension is equal to 4.0 kilograms. Oh, and you know what? This should have just been 2 sig figs. My bad. The 4.0 kilograms and the 6.0 kilograms are just 2 sig figs. But then we'll plug in that acceleration of 6.0 meters per second squared. And we can see that the tension is definitely going to equal, in 2 sig figs, 24 newtons. And so now we've solved both the acceleration as well as the tension as asked. So for our first pulley problem, we're going to see why pulleys often have what we call a mechanical advantage, where we can lift some heavy object by applying a much smaller force than the actual force that would normally require to lift that object. So here's a typical system of pulleys. So, and here we've got 3 lower pulley wheels that are attached to some object here weighing 24 kilograms. So, and then entire pulley system anchored at the ceiling. And the question is, going to involve, like, what tension do we have to apply here? So let's read the whole question. So what force must be used to pull the end of the cable to keep the 24 kilogram mass suspended in the air? All right, so let's take a look at this. All right, so if you see what's going on here, so just like in the example where we had 2 strings or 2 cables tied to a mast and they both applied a tension upward, the advantage here, where we get this mechanical advantage, is that there's the tension in the cable here is everywhere the same. So, and it's the mast here is attached to 3 lower wheels, and the cable interacts with those wheels twice at every single place. The way this works, so where does that cable pull up on the wheels? Well, it pulls up with a tension force right here, and 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 right here. It pulls up on these wheels in 2 locations each. And again, the tension in the cable is everywhere the same. And so whatever tension force we supply to this cable here by pulling down, it's going to actually be applied to lifting this mass or suspending this mass in 6 different locations. Now we also got this object's weight in our free body diagram. And so if we look, the sum of the forces, so since it's suspended, it's not moving. So, and not moving and definitely no acceleration means the sum of the forces equals 0, according to Newton's first law. And so if we take a look at those forces, well, there's 6 times that tension force all pointing up, so we'll make those positive, and then minus the weight, and that's going to add up to 0. So if we solve this for the tension, 6 times tension equals mg. Tension is going to equal mg over 6. So what we find out is that because it gets to pull up that tension in 6 different places, then the tension only actually has to equal 1/6 of the weight. So the way that's going to play out. And so in this case, we got tension is going to equal 24 kilograms times 9.8 meters per second squared, all over 6. And we'll let our calculator do the hard work here for us. So 24 times 9.8 divided by 6 is going to get us 39.2. In this case, we're going to round that down to 39 newtons for 2 sig figs based on the 24 kilograms there. And again, that's 39.2 rounding down to 39 newtons. Okay, so the second pulley problem says this. What is the acceleration of the 10.0 kilogram mass in the diagram to the right? What is the tension in the cable? So, and once again, the tension everywhere is the same in a cable. So it's going to be the same on both sides. And also these things are attached by that cable. And so the question's asking for the acceleration of the 10 kilogram mass, but again, they're attached. Their motion is coupled. Their acceleration is therefore going to be the same as well. Now, in this case, we can kind of deduce here, well, the 10 kilogram mass is heavier, so it's going to win. It's going to pull down this way, overcoming the weight of the 5 kilogram mass, which is going to pull down the opposite way. And so we know that for the 10 kilogram mass, the acceleration is going to be downward. For the 5 kilogram mass, it's going to be upward, but the magnitude is going to be the same. Their motions are coupled together. All right, now we've got 2 bodies, and this problem is what we call a 2-body problem, and you've got to set up a free body diagram for both, and then kind of net force equations, or some of the force equations, for both as well. Now this one's not going to be so bad. We'll see it's a little more challenging than the next one, but this one still has a key place where students make an error. We're going to avoid that error. All right, so let's start with the 10 kilogram one here. So it has got its own weight here, which I'll call mg, and then it's got a tension force pointing up, so as well. And if we do the sum of the force equation here, so in this case, again, we said this object is going to be accelerating downward. The forces aren't balanced, and so as a result, Newton's second law is going to apply, and the sum of the forces is going to equal ma. Now I'm going to stop there for just a second and set up the other one, and we'll come back to this. All right, so for the 5 kilogram mass, so also has its own weight pointing downward, mg, so, and it's got a tension pointing upward as well. Now we got a problem here. The two tensions are indeed the same. It's the same cable, and the tension in that cable is everywhere the same, but the mg's are not. These are different masses, and so maybe we more properly label these as like m1 here and m2 here, and then this becomes m2a, as we'll see, and we'll do the same thing, set up the sum of the forces for this one. Sum of the forces is going to equal m1 times a this time. And now we got to worry about one other major problem. So in the first example, we know this thing is accelerating upwards. Well, we generally define forces and accelerations that are upwards as being positive, so which is going to be the case here. And so the tension points up, we'll make that positive. The weight points downward, we'll make that negative. But the overall force and acceleration are pointing up as well. So this is going to be a positive term as well. And that'll be important, not so much here, but it'll be very important that we account for something in that regard over here. So, but we set up the sum of the force equation. We're going to have T minus m1g equals m1a. Okay, now we could say this is the sum of the forces in the y direction. We could, but we're not worrying about any forces in the x direction. There are none. And so there's only one set of forces, one equation for this particular body. So for the other one, we've got the same thing. So tension points upward will make that positive. So its own weight points downward, make it negative. But the big thing here is this, is we know the overall force and acceleration is going to be downward. And we've got to account for that here in the sum of the forces equation, the net force equation. Got to put a big fat negative sign there. If you miss that, that is the #1 mistake students make on such a two-body pulley problem. So, and again, it's just how you've defined things. If you're defining forces pointing up as positive and forces pointing down as negative, then the overall net force, you've got to account for it there as well. And so here we're going to have tension minus m2g equals negative m2a. So, and it turns out we can't solve for anything in either one of these equations. It's two equations with two unknowns. So let's put some of the variables in there. I'm going to leave off the kilograms, and I'm going to round this, I'll leave off some of the sig figs as well, just make this 5 and 10. So just to make the equations look a little simpler, keeping the units in can get a little bit tedious and complicated here. So, but we're going to have T minus M1 again is 5. So 5G equals 5A. And over here we're going to have T minus 10G equals negative 10A. So a couple different ways we could solve this. We could try and set this up with some form of linear combination, stuff like that, but my preferred way is probably just to solve this by substitution. So solve for one of the variables and substitute it into the other equation. So in this case, that's exactly what I'm going to do. And here, I'm going to make this solve for tension here. And here, adding 5G to the other side, it's going to be 5A plus 5G. So, and then I'm going to take and substitute that right in here. So for this tension right here, we're going to have 5G plus 5A. That's tension there. And then minus the 10G here equals negative 10A. And again, the accelerations are the same. It's the same A in both cases. So if we rearrange this just a little bit now, so 5G minus 10G is going to be negative 5G, and then negative 10A minus another 5A is negative 15A. And so solving for this, we're going to get A is equal to negative 5 over negative 15G, or 1/3 of gravity. And so we'll have 9.8 divided by 3, and we're going to get 3.2666666. And in this case, we want 2 sig figs based on the 5.0 kilograms having the fewest sig figs. So we'll round that down to round that up to 3.3 meters per second squared. right, so that's the first question answered. We've solved for the acceleration, and now we just need to go back to solve for the tension, either substitute that back in to this expression or this expression, and it doesn't really matter which one. And the truth is, we're probably going to be going all the way down to either here or here, let's say. And I'm going to substitute back in this one. The one I want, it's already solved for tension here for me. If it wasn't rearranged, I'd plug it back in here, but it's already rearranged like that for me, so life is good. So we're going to have t equals 5. Then we'll plug in that acceleration of 3.3 meters per second squared. And again, plus 5 times 9.8 meters per second squared. All right, so 5 times 3.3 plus 5 times 9.8. It's going to get us 65.5 newtons, which we're going to round up to 60. Actually, let's keep this back. If I didn't round early, I could do 5 times 3.266666666 plus 5 times 9.8, and I really should save the rounding for the end. That's going to be 65.333, which to 2 sig figs would round down to 65 newtons. Cool, and that's the second of the 2 questions. So this is pretty common on a two-body pulley problem like this, where you end up solving a system of equations, which throws students a little bit, but also getting that negative sign when the net force points downward for one of the objects, super duper crucial. One more problem. All right, so the last pulley problem here. So here's our setup. What is the acceleration of the 10.0 kilogram mass in the diagram to the right if the 5.0 kilogram mass is sliding on a frictionless surface? So no friction here, which is going to make this a little bit easier to treat and stuff like this. So, but notice the same masses here, 5 kilograms, 10 kilograms, 5 kilograms, 10 kilograms. A little bit of a difference here though. So if you notice, so the 10 kilogram mass was wanting to make the pulley, so in its weight was wanting to make the pulley rotate clockwise, whereas the 5 kilogram mass pulling downward was wanting to make it rotate counterclockwise. Well, the 10 kilogram mass was pulling with more force, overall weight, and so it won. Well, if we take a look at this one's a little bit different. So the 10 kilogram mass still has a weight pulling downward, m2g, that's wanting that pulley to rotate around clockwise. So, and again, there's still a tension pulling upward as well. But if we take a look at this guy here, so things are a little bit different in this case. So his weight points downward here, m1g. The tension pulls to the right in this case. So, and in this case, if we want to rotate this wheel back counterclockwise, we'd have to pull back to the left, not down. And so in this case, there's no actually pulling, force pulling back to the left. If there was friction, that would pull back to the left. It always opposes the motion. But we can see that this 10 kilogram mass is going to accelerate downward. That's going to pull the 5 kilogram mass to accelerate to the right. So, but there's nothing pulling back to the left. And so we got a little bit different setup here. So in this case, we got the 10 kilogram mass causing the pulley to rotate clockwise by pulling down, but this one's resisting it, trying to pull back the opposite direction. The acceleration ended up at 3.3 meters per second squared. Here, the 10 kilogram mass is still pulling downward at the exact same force due to its weight, but now there's nothing pulling back, if you will. It's still got a total weight of 15 kilograms to be moving around and stuff, but there's nothing pulling back. And we should anticipate that whatever the acceleration is here, and it should be, again, the same value for both of these, they're coupled motion here, but it should be higher than 3.3 meters per second squared since there is nothing pulling back. Let's see how this works. We've got one more force to draw in here, and that is the normal force here. Let's see how this problem works out. Now, in this case, the acceleration, again, of that 10 kilogram block. So, but again, whether you look at it as the acceleration of the 10 kilogram block, which is downwards, or the acceleration of the 5 kilogram block, which is to the right, magnitude-wise, it's going to be the exact same acceleration. Okay, so if we set up the sum of the forces for the 10 kilogram block first, it should look pretty familiar. Sum of the forces equals m2a, but we got to remember that the overall net force here points down, so we got to put that negative sign in there as well. And in this case, that's going to come out to t minus m2g equals negative m2a. Now, for the 5 kilogram, we've got forces in 2 different dimensions. There's technically 2 sets of equations to set up, one for the x, one for the y. Now, the one in which the acceleration exists is in the x direction here. So and maybe we should specify here that this is the sum of the forces in the y direction. This is the acceleration in the y direction. So whereas for this one, we actually want to set it up for the x direction preferentially. And the sum of the forces in the x direction here is going to equal m1a. Now it's customary for forces pointing to the right to be positive, and this is definitely going to be acceleration net to the right, so that's positive. And the tension is positive as well. That's the only force in this case, and so it's just T equals m1a, and they're both positive terms. Okay, not so bad. Now if we set this up for the y direction, and we technically don't need to solve this problem, it turns out, but if we did, it would look something like this. Sum of the forces in the y direction is going to add up to 0. In the y direction for this 5 kilogram mass, there's no movement, and therefore definitely no net force or acceleration. And so we're just simply going to have normal force, which is positive, pointing up, minus its weight, which is negative, pointing down, equals 0. And this would allow us to solve for the normal force if we needed to. And because there's no friction, we actually technically don't need to know the normal force. We don't even need this setup at all. It's available if we needed it, and if there were friction, we would. All right, so now we've got a system of two equations, both involving tension and acceleration. But again, this is the acceleration in the x dimension. This is in the y, and that seems a little bit odd. But again, remember that they're coupled, and the acceleration downward for the 10 kilogram mass and the acceleration to the right for the 5 kilogram mass in magnitude are exactly the same. And so we can take those labels off because it really is just one common acceleration as far as magnitude anyways. So the tensions are the same, it's just one cable, so the tension here and the tension here are exactly the same. And so it is the same set of variables in both cases as far as tension and acceleration go. Now if we want to solve a system of two equations again, I like substitution preferentially, so especially if one of the variables is always already solved for. So tension here is equal to m1a, and if we include some numbers here, that's going to equal tension equal to 5 kilograms times a. And I'm going to leave off the kilograms and some of the sig figs to make this look a little bit easier. So this equation over here becomes T minus 10G equals negative 10A. And because this one's solved for tension, we can take this 5A right here and substitute it in right here for tension to solve for A. And so in this case, we're going to get 5A substituted in for tension minus 10G equals negative 10A. And again, if you miss that negative sign, you're definitely going to get this one wrong. So we'll add 10A over to the other side here, and 10A plus 5A is 15A. So add the negative 10G, add 10G to both sides. That's going to equal 10G, and we'll find out that here A is going to equal 10 over 15 times gravity, or 2/3 times gravity. And we'll let our calculator do the work for us. So 9.8 times 10 over 15, or times 2 over 3 if you will, it's going to be 6.53, which will round down to 6.5 meters per second squared into sig figs. Cool, and our intuition proves correct here. We said that because this mass technically is not pulling back to try and make that pulley wheel rotate counterclockwise at all, that we should expect the overall acceleration in this case to be higher than it was back in this case. And lo and behold, that's true, 6.5 meters per second squared compared to 3.3 meters per second squared. Cool, if you found this lesson helpful, consider giving it a like. Happy studying.